We're going to part A of your unit test. Question number 1, or at least my question number 1, says magnets can be produced when small magnetic regions in a metal line up with their poles. These magnetic regions are called, this is the very first thing we did this unit, we call it magnetic domains. The domain theory of magnetism, these tiny little regions inside these ferromagnetic materials that when they're lined up, we have a magnetic material rather than just a ferromagnetic material. Question number 2 in my version says, given the magnetic fields illustrated above, the magnets will repel in which diagram? So 4 diagrams here. We don't even know what the poles of these magnets are, but we do know that in 2 of them, the field lines join up, and in 2 of them, the field lines don't join up. When they join up, we get a force of attraction. When they don't join up, we get a force of repulsion. So we're looking for which ones do not join up here, because we're looking for which ones repel. That's going to be diagrams 2 and 4. In diagrams 1 and 3, the field lines join up, so we get attraction. In 2 and 4, they don't join up, so we get repulsion. We get 2 bar magnets here of equal strength are positioned below. The direction of the magnetic field that they produce at point P is indicated in the diagram here. So we got a magnetic field that's up and to the right. Now, to get a magnetic field that's up and to the right, that means we have to have a magnetic field that's up and a magnetic field that's to the right. Well, what causes a magnetic field upwards? A north pole. Magnetic field goes away from the north. What causes a magnetic field to the right? A south pole. We get a magnetic field away from the north toward the south. That gives us north and south in this magnet, south and north in this magnet. The answer is going to be B for this one. Now, there's 2 questions that go along with this one. We got a cyclotron here, and we talked a little bit about a cyclotron before. We did a question actually real similar to this in a different context for our unit assignment. This question gives you the energy of a proton in electron volts. We're asked to find the maximum speed of the protons in the cyclotron. Now, in the end, as we learned when we went over our unit assignment, our temptation for a question like this, because the charged particle is going in a circle, our temptation is to go Fc is equal to Fm. And that's absolutely valid. mv squared over r is equal to qvb. It's absolutely valid for this question, but it doesn't get us the answer because we have too many unknowns. That's okay. Try it. If it doesn't work, try something else. What we're going to end up going with in this question is the energy. We have the kinetic energy of these protons. We want to find the speed. It's just like saying, look, I got a car that has this much kinetic energy, this much mass. What's the speed of this car? We would say EK is equal to 1/2 mv squared. It's no different. Rearrange this now to solve for speed. The 2 goes up by multiplying. The m goes down by dividing. And then, of course, we've got to square root that. Now, the only other thing is that we have the kinetic energy given to us in electron volts, and we have to find the kinetic energy in joules. So we're going to say 1 electron volt is 1.6 times 10 to the minus 19 joules. Remember how to do this, right? Conversion factors on your data sheet. 8 times 10 to the 4 electron volts equals x joules. So what we're going to do now is cross multiply. And when we do that, we end up getting x is equal to 8 times 10 to the 4 times 1.6 times 10 to the negative 19, right? We're taking the x up by multiplying and the 1.6 up by multiplying. And when we do that, for energy, we end up getting in joules 1.28 times 10 to the negative 14 joules, which we turn around now and sub into here. V is equal to 2 times 1.28 times 10 to the negative 14 joules, divided by the mass. And we're talking about the mass of a proton, so it's going to be 1.67 times 10 to the minus 27 kilograms. Don't forget to square root that. If you forget to square root that, you're going to get either D or A, those big exponents. You get an exponent that's bigger than 10 to the 8 meters per second, it's quite likely that you just forgot to square root. In the end, when we do this correctly, we end up getting 3.9 times 10 to the 6 meters per second, which if I had to predict, that's what I would have predicted, right? 10 to the 13, 10 to the 15, definitely both too big. 10 to the 8, possible, but not likely. That's also usually too big of an answer for us. Now, this next question, there's 4 possible answers that I accepted for this one because really it depends upon what you got for the previous question. If you got the wrong answer for the speed and the last question, you're going to get the wrong answer for this one as well. But we marked it right. So in other words, there's an answer for this next question that goes along with either A, B, C, or D, whichever one you picked. Now, how do we do this? Well, this is the one that comes down to the FC is equal to FM. We might have tried that in the previous question, but we ended up having too many unknowns. Well, let's try it in this question. MV squared over R is equal to QVB. We're looking for the value of the magnetic field. First, we cross off one of the V's, and we take the Q down by dividing. So B is equal to MV over Q times R. The mass of the proton, again, we're talking about protons here, is 1.67 times 10 to the minus 27. The speed that we got in the previous question was 3.9 times 10 to the 6. Although that speed you may have gotten wrong, and whatever speed you put in there would give you the correct answer. Would give you a correct answer, I should say. Now the charge is 1.6 times 10 to the minus 19. Because we've got an operation on the bottom, we got to make sure we use brackets on the bottom. 6.5 times 10 to the minus 2. So multiply those numbers on the top, divide it by bracket 1.6 times 6.5. When we do that, we end up getting 6.3 times 10 to the minus 1. So our answer here would be 631. But depending upon whether you had A, B, C, or D in the previous one, you could have gotten 246, 2.4 times 10 to the negative 6. You could have gotten 2.7 times 10 to the minus 1, or you could have gotten 1.6 times 10 to the minus 9. So any of those 4 answers would have worked. 631 is the correct one, but it depends upon you having the correct answer in the previous question. Next one, I think we might have seen this one before. I think we have an external magnetic field here that's directed into the page. We know that because of the X's into the page. We want to know what path 5 shows: a proton, a neutron, an electron, or an alpha particle. Now, in the end, this depends upon the charge of the particle, right? Whether it's positive or negative. We don't know. We got to guess. We got to guess here. So let's guess that it's a positive particle because proton's my first option. If it's a positive particle, we're going to use that right-hand rule for deflection, right? Right-hand rule for deflection. So let's say thumb in the direction of the particle in path 5, right here. Initially, the particle is going this way. So let's stick our thumb up this way. If we stick our thumb up this way and our fingers into the page, right? Thumb, fingers into the page, then our palm's going to point this way. Palm's going to point in the direction of the force, which is to the right and down, that is, which is going to cause this particle to deflect in the path 5 shown there. So this is... sorry, I just used my left hand. Look, just made a mistake. Actually, I said use your right hand because we're guessing proton. I used my left hand, and as it turned out, the left hand gave us the force that we were looking for there. Thumb, fingers, palm points in the direction of the force. So that must mean that my left hand was the correct one to use. Therefore, it must be an electron. I didn't do that on purpose. Yeah, just kind of slipped up. It was meaning to use my right hand, ended up using my left hand by mistake. So it is a negative particle, and the only option for a negative particle there is an electron. The next one, same box of information there. We want to know this time what path 3 shows. Path 3 is a straight line. And if we have something that's not deflected by a magnetic field, then that must mean that it doesn't have charge. And the only thing that doesn't have charge here is a neutron. Neutrons have mass. They're deflected by a gravitational field, but they don't have any charge, so they're not deflected by a magnetic field. These are answer for this next question. Next one. A magnet moves into a coil of wire shown below. As a result of this motion, a current is induced in the coil and a magnetic field is produced. This is the Lenz's law thing. If you remember, we said that in Lenz's law, we have a magnetic field number 1. That would be this magnetic field right here. Magnetic field number 1 is going to cause an electric current. Okay, there's going to be an electric current induced in this coil. We don't know which way that current is yet. That's okay. We'll figure that out. That electric current generates a second magnetic field, B2. Now, that second magnetic field, along with the first magnetic field, have to act together to oppose the motion. Otherwise, it would violate that law of conservation of energy. So what's the polarity of this coil got to look like in order to oppose the motion? Well, if we pretend there's a little bar magnet inside, it would look like this with a north pole this way. Look, this magnet is moving downwards. In order to oppose the downward motion, we need a magnetic force upwards to oppose it. And the only way to cause a magnetic force upwards is to have a north pole up there. Now, if the north pole is up there and the south pole is at the bottom, the magnetic field goes from south to north inside the coil. We're going to do our coil rule here. I'm going to stick my thumb up from south to north, and in the front, my fingers are going to point towards the left. So my current in the front is in the direction of my fingers towards the left. So I'm going to draw that in right here. In green, the current, sorry, I got that drawn the wrong way again. The current in the front is drawn towards the left. So we got a current in the front to the left. That must mean the answer is either C or D. Which way is the magnetic field? Well, the magnetic field goes outside of this coil, away from the north and toward the south. So the answer is going to end up being C for this one, right? Current to the left in the front, and the magnetic field going from north to south, from the top to the bottom, outside of the magnet. So my answer is C. And the next one, this is a coil rule as well, but not Lenz's law this time. This time we just have a solenoid, and we want to find the magnetic field inside the solenoid. I'm going to use the electron current, and therefore, since I'm using electron current, it's going to be the left-hand rule, the left-hand coil rule. My current goes this way, up in the front, and it's going to end up going down in the back. I'm going to say my fingers are going to point up in the front, and my thumb will automatically point towards the right. My thumb's automatically pointed towards the right, so the magnetic field inside this solenoid is to the right. Looks like this. The answer is going to be D for this one. More fields. This time we have an electric field and a magnetic field and a gravitational field, and we want to know which one is which. We know that in this question, all three of these fields are causing an electron to be deflected downward. We want the electron to be deflected downward. Well, the easiest one to figure out here is a gravitational field. Electrons have mass, and if they have mass, they're deflected in the direction of the gravitational field, right? This board marker, if I drop it, it accelerates, it deflects in the direction of the gravitational field. So because the force of gravity is always the same direction as the gravitational field, gravity is the easiest one to deal with. That means field number 3 has got to be the gravitational field, right? This particle is deflected downward in a downward field, so it must be gravity. It's the only field where a negative particle is deflected in the direction of the field. Now, the electric field is the next easiest one. A positive particle is deflected in the direction of the electric field. I'm positive the force is with the field. But if it's a negative particle, it's deflected opposite to the direction of the field. So which way is the electric field pointing? To cause a downward electric force? Well, if the force is downward, then the electric field must be upward. So field number 1 is the electric field. Now, that must mean field number 2 is the magnetic field, but let's just double check that. This is a negative particle, so I'm going to use my left hand deflection rule, thumb in the direction of the particle, fingers in the direction of the field into the page, palm points downward. Sure enough, the deflection of the negative particle in a magnetic field pointing into the page would be downward. So field number 1 has got to be electric, number 2 has got to be magnetic, number 3 has got to be gravitational. Means the answer is going to be A for this one. 14. In an apparatus such as this one shown above, the direction of the magnetic field at point P due to the electron flow would be which way? Now, there's a couple ways to do this. Some people probably use the coil rule for this. I would not recommend that for this one, although it would work if you did it properly. I would suggest just the wire grasp rule. And it's going to be, because we're looking at for electron flow, it's going to be the left-hand wire grasp rule. I'm going to just look at the direction of the moving charge right here. Right here. The charged particle is moving downward at this point. So what I'm going to do is say thumb in the direction of the particle, fingers are going to point in the direction of the magnetic field directly to the right of that particle, which is going to be into the page there. So thumb downward at that point, fingers into the page. The answer is going to be A for that one. Magnetic field surrounding a current in a wire. We're talking about electron current here. So if we're going to use a hand rule, this is going to be a left-hand rule. Now, in the end, there's two things that you've got to recognize for this question. First of all, you've got to recognize that magnetic field is defined, or the direction, I should say, of the magnetic field is defined as the direction that a compass points when placed in the field. So these four compasses are all pointing out of the page. The magnetic field is not pointing out of the page in all four places. So not all of these compasses are pointing in the right direction. Which of these four compasses is pointing in the direction of the magnetic field? That's the first thing that you got to recognize. Compasses point in the direction of the magnetic field. Second thing is, which way is the magnetic field? That's the wire grasp rule. If we use the wire grasp rule for this, thumb up the page, fingers wrapped around like this, thumb up the page, fingers wrapped around like this, then the only situation where my fingers are pointing out of the page would be to the right of the wire, right? In front of the wire, my fingers are pointing to the left. To the left of the wire, my fingers are pointing into the page. Behind the wire, my fingers are pointing towards the right. And to the right of the wire, my fingers are pointing out of the page. So the only one that is correct would be 3. Number 1 is pointing out of the page, but it shouldn't be. It should be pointing into the page. Number 2 should be pointing to the right. Number 3 should be pointing out of the page, and it is. And number 4 should be pointing towards the left of the page, but it isn't. It's pointing out of the page. So my answer for this one is going to be 3, which is option C. Next one. Next one's kind of ugly because you had to do 4 things for this one. We have 4 diagrams here: an electric field, a magnetic field, an electric field, and a magnetic field. And we had to identify the direction of either the electric field or the magnetic field in all 4 cases. So let's look at the first one. The direction of the electric field in diagram 1. Look, electric fields point away from positive toward negative. If this is my battery, then this plate becomes negative, this plate becomes positive, and the electric field is going to point from positive to negative, which is to the left. So my answer for the first one is 4. My electric field points to the left. Now, the next one is a magnetic field. It's into the page, electrons going into the page, left hand, wire grasp rule, thumb into the page, fingers are going to wrap around like this. So at this point, the magnetic field is going to be pointing downward, which is going to be option 6. So the magnetic field pointing downward, option 6. The third diagram, we have an electric field again. We're looking for the direction of the electric field caused by that positively charged sphere. The electric field points away from positive toward negative. So the electric field at point P is pointing down and to the right, which is option 1. And finally, the magnetic field in diagram 4. A number of you made a mistake on this one. Just out of carelessness, I think. Look, we got an electron current. An electron current going this way, to the left in the back, to the right in the front, goes around like this, wraps around like this. We're going to use the coil rule for this one again. My fingers are going to point to the right in the front, and my thumb's going to automatically point downwards. So if my thumb points downward, the magnetic field inside this coil is downward, but outside this coil at point P, it's going to point upward. A lot of you put 5 for that one because you recognize that the magnetic field is pointing downward, but that's inside the coil. We're looking for the magnetic field outside the coil. So my answer for this one would be 5, I should say. 4, 6, 1, 5, upwards. (17) A graph shows the relationship between the radius of curvature of a hydrogen ion's path and the strength of the magnetic field. Look, I told you when you're trying to find a relationship, whether it's in words or whether it's in a graph, you want an equation for this, right? So let's say FC is equal to FM. This is going to give us the relationship between R and B. So we got MV squared over R is equal to QVB. V's cancel. Solve for R here. The R goes up, the QB goes down. Becomes MV over QB. Now we're looking for the relationship between R and B. That's an inverse relationship. R is related to 1 over B. And a graph that reflects that would be option D. The only one that shows an inverse relationship is option D. Next question says, a stream of electrons with a given speed enters a magnetic field of known intensity. The direction of the motion of the electrons is perpendicular to the direction of the magnetic field. That just means that all the equations and hand rules that we've learned applies if it's perpendicular. Changes are made to both B and V. The radius of the circular path will always increase when. This is another relationship between variables question. It's just not a graph, right? It's more of a word problem. So we need an equation that describes this. And that equation, once again, is the same one that we just derived. R is equal to MV over QB. Which comes from FC is equal to FM. The centripetal force is equal to the magnetic force. Now, when is R going to increase? R is going to increase if M increases, or if V increases, or if Q decreases, or if B decreases. So Q and B have to decrease in order to increase R because they're inversely related to it. They're on the bottom, the denominator. So which one matches up here? B increases, no. B increases, no. B decreases, and V increases. Yes, that's the one. So my answer for that one is C. And the last question on the multiple choice, at least in my version, says almost all electric guitars use devices called electromagnetic pickups. A guitar string is composed of metal that becomes magnetized by a permanent magnet found below the string. So the string is a magnet. The string becomes a magnet because of our permanent magnet. It's magnetized. First day of this unit, we talked about how things become magnetized. Bring a permanent magnet nearby, it becomes magnetized. So the string is a magnet. Now, it says a coil of wire surrounds a permanent magnet. When the string is plucked, a small current is produced in the coil. This is electromagnetic induction, Faraday, right? The generator effect. When do we get an electric current generated? Well, we have to have a wire and a magnetic field. Here's my coil of wire. Here's my magnet. Now, there's one of 3 things that has to happen. You can move the wire. I'm not doing that here. This coil of wire is not moving. I can move the magnetic field. That's what I'm doing here, right? This guitar string is the magnet, and it's moving up and down. So as that magnet, this magnet right here, that is the guitar string, moves up and down, it generates a current in the coil. The third thing that we can do that doesn't apply here is change the strength of the magnetic field. So it's option number 2 that's working here. Let's find an answer that kind of matches up with that. Ends up being D. The string behaves as a magnet moving toward and away from the coil. Now, let's take a look at the second part of this now. the written response part of this test. Which should go fairly quickly for us. I think there was only 5 questions. Couple different versions of this. I'm going to do it as if from version 1. If you had version 2, your numbers will be a little bit different, but the methods will be exactly the same. Question number 1 here says, determine the direction of the magnetic field at point P caused by the electrons moving the wire. Look, thumb points toward the right of the page. Fingers are going to point into the page. So my answer is just going to be into the page. That was worth 1 point. That's just a wire grasp rule, right? The left-hand wire grasp rule, because we're talking about electron flow. Now, number 2 says a current carrying wire, current carrying conductor that's 4 times 10 to the negative 2 meters long is placed perpendicular to a magnetic field that has a strength of 6 times 10 to the negative 2 Tesla. During 20-second interval, 7 times 10 to the negative 10 to the 19 electrons pass a point in the conductor. What's the magnetic force here? So what we're going to do for this one is say, look, F is equal to ILB. The magnetic force on a wire is I times L times B, but we don't know what I is. That's fine. We'll get it. The current is Q over T, the charge over the time, but we don't know what the charge is, and that's fine. We'll get it. The charge is the number of electrons, 7 times 10 to the 19 electrons, times the charge of 1 electron, 1.6 times 10 to the minus 19 coulombs. We multiply those together. We get a value for the charge. I'm not sure what I have there, because I don't have that calculated. Let's just pull out the calculator for this one. 7 times 10 to the 19 times 1.6 times 10 to the minus 19. That gives me 11.2 coulombs, which are going to sub back into here and divide by the time of 20 seconds. And that gives us a current of 0.56 coulombs per second, or 0.56 amps, which we're going to sub back into here and multiply by the length and the magnetic field. And when we do that, we should get a 1.34 times 10 to the negative 3. Let me do my substitutions here, actually. 0.56 amps times L, 4 times 10 to the negative 2, times B, 6 times 10 to the negative 2. And that gives us 0.56 coulombs per second. Sorry, that's wrong. 1.34. Looking at the wrong number there. 1.34 times 10 to the minus 3 newtons. And that was worth 2 points. Pause that if you need to copy that down. Number 3, an alpha particle travels in a direction perpendicular to a magnetic field of strength 1.6 Tesla. The alpha particle experiences this force. What's the speed? This is a pretty straightforward one. If you recognize that this is an alpha particle, we're going to say F is equal to QVB. We're just going to rearrange that now to solve for speed. The Q and the B both go down by dividing, so it becomes F over Q times V. My force here is 1.1 times 10 to the negative 13 newtons divided by my charge, 3.2 times 10 to the minus 19, because it's an alpha particle, and the speed is, that should be Q times B on the bottom. The magnetic field is 1.6 Tesla. Make sure you use brackets on the bottom of your calculator, right? Because you're doing an operation. So 1.1 times 10 to the negative 13 divided by bracket 3.2 times 10 to the minus 19 times 1.6. And that gives us an answer of 2.1 times 10 to the 5 meters per second. 214843, 2.1 times 10 to the 5 meters per second. That one was also worth 2 points. Pause that again if you need more time to copy that. 4, when an electric current of 10 amp flows through the wire, travels through the wire, there's sufficient magnetic force to keep the wire suspended against gravity. What's the magnitude of the magnetic field necessary to do this? I know that some people were asking me about this, the resistance of the wire. You actually did something like that in grade 9 science with resistance and ohms, but that's irrelevant for this question. And we've talked about that before. If you see something that you've never seen before or you haven't learned in Physics 30, don't worry about it. It's not part of the solution to the question. The key word here is suspended. If it's suspended, we're in a state of equilibrium. And if we're in a state of equilibrium, then forces must balance. I'm going to balance the gravitational force and the magnetic force, or I'm going to say M times G is equal to ILB. We're looking for B. So B is going to be equal to the I and the L go down by dividing, mg over I times L. My mass here in kilograms is 0.85 times 10 to the minus 3 kilograms, right? We're given the mass in grams. We tack on a 10 to the minus 3 in order to make that kilograms. Times that by 9.81. The current here is something, 10 amps. And make sure you have that in brackets on the bottom. 0.013 meters. That's going to be in meters, not centimeters. So multiply the top, divide it by the bottom, but make sure that bottom is in brackets. And when we do that, we should get 6.41 times 10 to the negative 2 Tesla. And that's pretty reasonable magnetic field there, 6.41 times 10 to the negative 2 Tesla. And finally, the last question, number 5. Solar wind, particles of the sun. Here's a speed, here's a magnetic field. That's a pretty weak magnetic field, actually, but far away from the Earth. That's reasonable. We want to determine the direction of the magnetic force on the protons on the solar wind. It's protons, so this is going to be a right-hand rule. Magnetic force, this is going to be a right-hand deflection rule. So how do we do this? Thumb in the direction of the particle. As the solar wind enters the Earth's magnetic field from the left, my thumb is going to point the way that it's going towards the right. But my magnetic field is pointing toward the top of the page. Look, particles moving towards the right, magnetic field at that point pointing toward the top of the page. So thumb towards the right, fingers toward the top of the page, palm is going to point out of the page. Thumb to the right, fingers up the page, palm points out of the page, using my right hand because it's protons. So my answer is going to be thumb, fingers, palm out of the page. My magnetic force is going to be out of the page. And finally, very last question here. The direction, the radius of the circular path that the protons follow. We've used this equation a couple of times in our test now in the multiple choice portion. We're going to say FC is equal to FM, or mv squared over r equals qvb. V's cancel. I get mv over r equals q times b. Solving for r, so the r goes up by multiplying, and the qb goes down by dividing. It becomes r is equal to mv over q times b. The mass, because we're talking about protons here, is 1.67 times 10 to the minus 27. The speed is given to me as 8 times 10 to the 5. And we divide that by, again, brackets on the bottom, right? Because we're doing an operation. Q is 1.6 times 10 to the minus 19. And the magnetic field strength there is 1.1 times 10 to the negative 7 Tesla. So let's do this final one on the calculator here, just to remind you of the need for those brackets. 1.67 times 10 to the minus 27 times 8 times 10 to the 5. And now let's divide that by brackets on the bottom. 1.6 times 10 to the minus 19 times 1.1 times 10 to the minus 7. And when we do that, we get 75909 rounded to 3 digits. That should be 7.59 times 10 to the 4 meters. Some of you actually put 7.60. It should be 7.59, but I got a little soft and marked 7.60 correct. That's it. Do those corrections, copy them right out from this podcast, 5-point bonus on that unit test.